Elements of programming interviews for that one, computing the parity over Word version 4. There are two major ways to improve performance of a bitwise, bit fiddling operations. One of which is using a cache. In the previous version, we use an array-based cache to look up pre-computed parity values. Another approach is to be able to look at multiple bits at a time, process multiple bits at a time to improve performance of a bitwise operation. So this particular example is going to be solving it via using multiple bits, looking at multiple bits at a time, using, taking advantage of CPU's word level XOR instructions. We are able to do this because parity calculation is associative and commutative. It doesn't matter, how the bits are organized. Because for parity, you really care about how many set bits are there. It's either or even or odd number of bits. It's commutative. It doesn't matter how you apply the XOR instructions, whether the first number comes first or second number comes first. It doesn't matter. So because of these properties, we are able to take advantage of CPU's word level XOR instructions, and that reduces actually number of steps it would take to calculate the parity of a given binary word. So here we have an example where we have this 8-bit number, and what we're going to do basically is that we're going to take the first 4 bits and XOR that with the second 4 bits. So 111101 XORed with 0111, which will give us the result as 1010. So how does that work? We take this least 2 bits, 1 XOR with 1 is 0. We take this bit and XOR that with this bit, we get a 1. We take this bit and XOR that with this bit, 1 1 0, and then we are taking the first bits and XORing it, we get a 1 0 1. Just a reminder, XOR instruction, when the 2 bits are the same, you get a 0 in the case of 1 1 and 0 0, and if they are different, you get if they are different, then you get a 1. So now we got 1 0 1 0. What we're going to do next is we're going to take these 2 bits and XOR that with those 2 bits, and our result will be 0 0 0 and 1 1 0. So now we have 2 bits left. We XOR with these 2 bits and we get a 0. And if you look at the number, how many bits there are, 1 2 3 4 5 6, there are even number of bits, and it makes sense that parity is 0. One thing to call out, as we are actually calculating parity, like when we take the 4 bits and the least significant 4 bits and the most significant 4 bits, when we XOR that, we get, as we calculated this number here, 1010, but we still have numbers 4 bits before that, but we don't care about that. We only care about the last 4, and then in this case we only care about the last 2 bits. In this case we care about the last single bit, which will tell us the parity. So when we define it, define parity, we take an x. What we're going to do is we're going to take x and we're going to XOR x with itself by shifting x by 32 bits. Because it's a 64-bit integer, what we were doing is we were looking at 32, we XOR with that number, and as a result we're going to get a 32-bit number. So we take that x and XOR that with x shifted by 16, because now we're going to look at this 16 bits by 16 bits, just like each time we are dividing it by half. Now we take x, XOR that with 8, we take that x and we XOR that by 4, we take that x, we XOR that by 2, and of course we take that, and so 1 2 4 8 16 32, these are the this is how we are shifting. And at the end, when we are done, we're going to return taking our x remaining by XORing, and that ended with 1. And the reason why we are doing this is because, as I said, at the end we really care about the least significant bit which has a result, and in order for us to get that, we basically end this is our bit mask, right? let's assume that this number was, you know, actually X ended up being like, it's 64 bits, but I'm going to write like least significant 5-6 bits, 1010011, I'm sorry, 1010101, and in order for me to get this least significant bit, I'm going to end it with 000 whatever 1, and I get that number via that operation. So that's what we're going to return at the end. I hope this makes sense.